As we saw earlier, energy data can come from many different sources. However, choosing one source over another can lead to substantial differences. And it's important to keep this in mind when analyzing data. Let's explore this through a practical example. We compare photovoltaic energy yield from two widely used sources, PV-GIS and Renewables Ninja, for the same site, Vercelli in Italy. First, we start with PV-GIS, the Photovoltaic Geographical Information System by the European Commission's Joint Research Centre, so JRC. Enter Vercelli, Italy, in the location bar or select it directly on the map. Choose the SARA3 database, which is based on satellite-derived data covering Europe, Africa and the MENA region. It offers higher spatial precision than ERA5. Set both the start and end year to 2019, which ensures comparability with Renewables Ninja, which currently provides data only up to that year. This is important to exclude the impact of meteorological data from the analysis. Choose the fixed mounting type, so no tracking, and select a slope of 35 degrees and an azimuth of 0 degrees. You need to tick the box at PV power to obtain the output energy production of the plant. Use crystalline silicon as the PV technology and leave the other values as default. Also, tick the radiation components box, which allows to get better insights when analyzing the data later on. Now you can simply click on CSV to download the 1-year radiation data and electricity production from PV-GIS. You receive a full year time series, including irradiance, temperature and AC energy output. Great! You've just seen a very simple but powerful way to calculate PV potential. If you want to go a step further and repeat the analysis multiple times, there's a very well documented API which can be easily integrated into Python. Now let's move on to the second data source, Renewables Ninja, which is widely used across scientific literature. To run the same simulation in Renewables Ninja, go to Renewables Ninja website and select PV tab. Again, enter Vercelli as the location. For the dataset, choose MERA2. This is a reanalysis dataset with global coverage, although it has a lower spatial resolution compared to SARA3. Set the year to 2019, just like we did in PV-GIS. For the same system size, enter 1 kilowatt. Then set the system loss fraction to 0.14 or 14% to match the default assumptions in PV-GIS. Set tracking to none and tilt to 35 degrees. For the solar azimuth, be careful. Renewables Ninja uses a different convention than PV-GIS. Here, an azimuth of 180 degrees corresponds to south facing. So while we use 0 degrees in PV-GIS, we need to use 180 degrees in Renewables Ninja to achieve the same orientation. Finally, tick the box labeled Include Raw Data and then click on Run. After a few seconds, you'll be able to download a CSV file with hourly data for the entire year. At this point, we've downloaded solar profiles from the two separate tools. We used nearly identical assumptions, and now let's compare them. I did some pre-processing and analysis of the output data, which you can see here. We observed some notable differences. First of all, there's a consistent discrepancy in total annual energy production, which is around 5%. This is not a trivial difference, especially when you're looking at a scaled, full-size PV plant. And it's important to emphasize that all adjustable variables like tilt, orientation, capacity, losses were configured to be equivalent in both simulations. Digging deeper, we also see difference in the maximum power output. This is interesting because both models were based on a system size of 1 kilowatt peak. The fact that the peak power varies between the two tools suggests that different inverter assumptions are being used. In particular, different AC-DC ratios or clipping thresholds. It's likely that PV-GIS allows for a higher instantaneous output, while Renewables Ninja applies a more conservative inverter cap. Looking at the monthly energy breakdown, we calculate what's called the seasonality index, so the ratio between the most and the least productive months. In this case, the seasonality index is higher for Renewables Ninja. This suggests that the model exhibits stronger seasonal swings in the production. This supports the hypothesis that the lower annual lead is not primarily due to clipping, but rather to a general underestimation of energy production throughout the entire year. The different productivity could be associated to many different reasons. Differences in radiation data, in spatial data resolution, modeling differences on the influence of temperature, handling of diffuse radiation, and many more. We can also see these trends reflected in the average daily production curve. When we plot the mean power profile across all 24 hours, we notice that Renewables Ninja output tends to peak slightly earlier in the day compared to PV-GIS. This may seem minor, but it's an important technical detail. PV-GIS associates each hourly value with the end of the hour, whereas Renewables Ninja uses the center of the hour. So for example, a PV-GIS value at 2 o'clock represents energy from 1 to 2 o'clock, while Renewables Ninja places the same energy interval at 1:30. If you are not aware of this, it can lead to misleading conclusions when aligning datasets or comparing profiles. So what can we learn from this? Even in a relatively simple modeling scenario, 1 site, 1 year, 1 kilowatt, there are multiple subtle factors that influence the final output. The tool we've used are both very powerful and freely accessible, and they offer excellent starting points for preliminary assessments. But the difference underlines the need for critical thinking. We can't treat energy data as a black box, and we need to understand where the data comes from, how it was processed, and what assumptions are embedded in the model. If greater precision or control is needed, for example in a pre-feasibility study or financial assessment, more advanced software is often used. One such tool is the System Advisor model, developed by NREL in the United States. SAM allows you to specify every aspect of the system, from the PV model and the inverter specs to hourly loss factors, grid constraint, and detailed financial parameters. While it's more complex to use, it offers a level of customization and transparency that is essential for high-quality engineering and investment-grade analysis. In short, tools like PV-GIS and Renewables Ninja are excellent, but as always, it's not just about using the tool, it's about understanding how it works, what it's good for, and where its limitations lie.